Okay, let's get started. So there are several new students. There's a WeChat group for this course. If you haven't entered a WeChat group, you can ask the person next to you and then enter the WeChat group. Last time I made a mistake in the derivation of the geodesic equation. So let's recap briefly. So this is the length action, and I treat this one is the geodesic. To derive this one, so I treat this one is the Lagrangian, and all our Lagrangian equation is this guy. And then recalling that the L, so we just treat, let's see. So this d tau square is equal to g mu nu dx mu dx nu. Then so therefore L is in fact d tau over d lambda. D tau over d lambda. Then so if you write down everything in terms of so then plug this one into here, what you get is that the d lambda and then g mu nu and then a derivative of metric rho sigma and dx rho d tau and dx sigma d tau. Here dot means the derivative with respect to lambda, but now it becomes the derivative with respect to tau. Okay, and then just this guy is in fact just using Leibniz rule. We can just write down that the so this is in fact the partial alpha g mu nu dx alpha. It's just Leibniz rule. Dx d nu d tau and then g mu nu and then d square x nu d tau square. Okay. And then so this one can be just write down like this way. So from here g mu nu d square x nu d tau square is equal to 1/2 derivative of the did I write down 1/2? No. Yeah. Sorry, there's a 1/2 here. So there's a 1/2. Yeah, sorry. There's a 1/2 here. Sorry. Yeah, this is 1/2 here. And then, so what we have is that g mu, g rho sigma, and dx rho, dx sigma, d tau. And then we'll have the derivative. And then we have partial alpha g mu nu dx mu dx tau dx mu dx tau. Okay, so that's what we have. And then using the swapping indices and so on, what you get is that the swapping indices that what you get is that the d square x mu d tau square plus gamma mu nu rho dx mu d tau dx rho d tau is equal to 0. Where the gamma, this guy, is defined by g mu sigma 1/2 partial g plus partial g minus partial g nu rho and sigma nu rho and then nu sigma rho. Okay. So that's the derivation. So last time I didn't do that correctly. so this is the correct derivation. And then So we start with the Einstein-Hilbert action, d for x squared minus g r minus 2 lambda. And then with respect to variation of the metric, the last time we just showed that this one will give you famous the Einstein equation r mu nu minus 1/2 g mu nu r plus the what was that? Lambda g mu nu is equal to I think I need to multiply some appropriate number, c cube 16 pi g. Okay, and then the right hand side is equal to 8 pi g divided by c to the 4 g mu. So that's what you derived last time. Unfortunately, since I disconnected some cable in the middle last time, the recording was not of the video is not available. I'm very sorry about it, but hopefully this time it's okay. Okay, so that's the derivation Einstein equation, and then from now on, so we will use this Einstein equation to understand the nature of space-time. Okay, so as I mentioned, so there are several new students. So there's a WeChat group for this course. If you haven't entered, so you can just ask students next to each other and to enter it. Okay, so that's the case. So this is like people mentioned that this is a very beautiful equation. I mean, it governs the energy, just determine the energy, or whatever matter will determine the curvature of the space-time and so on. But only looking at this one is not so meaningful. So we have to use it. And then the entire course is actually more than like 2/3 of this course is to understand what this equation means in many circumstances. That's the purpose of my course. Do not oh, this is beautiful, and just look at it. It's meaningless. So we have to use it once you derive the equation. So that's what we are going to do. But before that, let's talk about something like a fate of star. So before that, mostly we would solve this equation. But before that, we would talk about let's talk about the fate of star. Fate of star. Okay. So like if you encounter like a sun or like a star, they are just like burning the hydrogens and also helium and so on. And eventually, if the people gets old, as people gets old, somehow even star also can get old, and it starts creating so-called iron in the middle. And then iron in the middle, and then there's a layer of lots of composite. This is the next is silicon and so on. Anyway, some magnetism and neon, oxygen, and the carbon and so on. There's a layer of the material which you see in periodic table. And eventually, they lose the power of the burning. So you cannot, burn the iron and so on. So eventually, so there is this gravitational force, corruption. The force of gravitational collapsion will win versus this burning pressures. So that's so this is around 10 solar mass, the end of the 10 solar mass star, like this way. Eventually, this gravitational collapsion attraction will win against this burning pressure, so they will encounter like a how to say the collapse gravitational collapse, and then so-called you encounter so-called supernova. And after that, the star will become the following thing. So eventually it becomes supernova. Then after that, the core of star will remain. And if the mass is not big enough of the star, it becomes the so-called the white dwarf. So if mass is not big enough, so it becomes dwarf, white dwarf. So in this, so as I mentioned, so the white dwarf is actually last time the one solar mass, and then radius is around like a 6,000 kilometers. Which is around the size of the Earth. So that you can just squeeze the sun into the size of the Earth, and then in that like a white dwarf. So in fact, so that there is some so gravitational force, attraction, is the how to say against so-called electron. So it's a very dense electron degeneracy pressure. So they just so this is so the gravitational attraction, again they try to destroy the star or like contract the star, but so as you know, Fermi electrons obey the Fermi statics, so that they try to how to say against the gravitational force. And let's estimate how much this electron pressure is, and then when these two forces become equilibrium. Okay? Let's make an estimate. That's what the Chandrasekhar did a long time ago, when he was like 19 years old, from in the ship from the India to the England. So the quantum length of the electron, let's make an estimate, is around like this, NE minus 1/3. So quantum length NE is actually the how to say the NE is the number density of the star. Density of the electron. So therefore NE is actually that how much. So if you have a cube, so there's the one electron. So one electron is here. One electron is here. E. Let's go E. And then so here you have the roughly length is n minus 1/3. NE minus 1/3. And if you just make a cube and then multiply the r square and so on, if you cube, so you have a volume of roughly one electron. Okay, 1 over NE is the number density, is the roughly volume of the volume of the space that one electron can take. And this one can be it can be understood as quantum length. So therefore we can just have a to the PE. So P is the average. So this is the expectation value. Expectation value of momentum. Okay, of electron. So this is the rough the quantum length. And then so we consider that the electron is relativistic. So therefore, and it's very tiny mass. So therefore, energy is roughly the PE C, so which is around h bar C and E minus 1/3. Okay, so that's the rough estimate one can just make. Okay, so you just use this equation to plug into PE. Okay.
What's the 1/3?
Huh? So thank you very much. Positive 1/3. Okay. And then, so this is rough, like each electron has the average energy like this way. And we know that in star, so this is EE. Let's go. So the E of kinetic energy of the star is the, each electron has this, the energy, average energy. And we know that the number of electron is the number density times R cubed. Okay, so this is the number. So this is the number of number of electron. Okay, and then this one. So if you plug this one into here, what you get is that the h bar C R cubed and E 1/3. Okay, so you just plug this one into here, and then you get this one. Okay. And you can use the following fact. So the number density is the total mass of the what was it? The star, and then you can just divide it by number of the. So that you can just number density of electron is total mass divided by ME times R cubed. Then you plug that into here, and what you get is that the, sorry, not ME, MP, sorry, MP. Because I mean, most of the MP is bigger than the ME. So the electron mass is much smaller than proton mass. So therefore, you have to divide it by, so the most of the star mass come from proton. Okay, so therefore, so number of density, if you pair the how to say, neutron and electron, or even here a proton and electron, and they become neutral, then the electron density can be estimated like this way. And then plug that into here, what you get is as follows: is equal to h bar C and then m over m proton 4/3 1/r. Okay, so if you plug that one into here. So this is the kinetic energy due to the electron density pressure. Okay, and that will how to say? So when does the equilibrium sorry, my English is become rusty. Equilibrium happen is that the gravitational potential is of course G times m squared over R, and then which becomes equal to Hc m over me 1/3 1/r is equal to 0. So this is when the MP. Thank you so much. Okay, so when the gravitational force is become equal to the electron degeneracy pressure. Okay, so then we can just make an estimate that so from here, so the maximum mass which can just occur for the neutron, not neutron, white dwarf is the 3/2 and 1/mp squared. Okay, so that's what's really happening. So you just solve in terms of m in this equation. What you get is this one. Okay. What you get is this one. I mean, just a straightforward exercise, which I'm not going to go to do that. Then this is, if you substitute all the numerical value of this one, this is indeed equal to 1.4 our solar mass. Okay. That's what Chandrasekhar did for in the ship. So this is called Chandrasekhar limit. Chandrasekhar most likely you're right. Yeah, you're right. Okay. So thank you. So if you make a mistake, please point me out. Okay. So this is the. Okay, and then so we know that the compound length is the roughly the h bar c over mass of electron, which is Ne minus 1/3. Then this is equal to mc divided by mp rc cube divided by minus 1/3. Okay. So this is the rough estimate of this radius versus mass. C means the really Chandrasekhar C, coming from Chandrasekhar limit, the maximum mass. So, and this one will give you RC is equal to roughly NE NP. So this is the mass of the radius of the white dwarf, maximum radius of white dwarf. Okay. So this is the roughly rough estimate maximum radius for white dwarf. Okay. So this limit is roughly slightly bigger than this number, but the order is the same. So this RC is the order is slightly bigger than one solar mass. You get the size of roughly R. So therefore, slightly bigger, but the order is the same. Okay. It's just multiply 1.4 around of this. Okay. So this is 9031, and then the question is what's going to happen if the star white dwarf has a bigger mass. Okay. So then gravitational attraction will win against the electrodynamic pressure. Okay. And the people propose the following thing. So instead of electrodynamic pressure, people will start thinking about the so-called neutron. So this is the neutron, sorry. Neutron. Degeneracy pressure. Okay. So then, so one solar mass, as I mentioned last time, is roughly radius is in fact 10 kilometer, only 10 kilometer, roughly. So the less than the size of the Shanghai. So just going from essentially from here to whatever. Center of Shanghai is the most likely more than 10 kilometer, so that it's a very, very dense object. So what's going to happen is that in this kind of like a bigger star, is that instead of like electron degeneracy pressure, so they start forming like this kind of reaction, ignite this kind of reaction. Okay. So electron and the proton has the negative and positive charges, and they become the neutron after this. Okay. So this process is in fact does not occur unless you have a very, very high pressure, because there's a NP, so NM is NP is positive. Okay. Slightly neutron is bigger than the proton. So therefore, to get the difference, so you need the energy, which is let's call this one is delta M and P. So you need some energy of this delta M and P to how to say trigger this reaction. So therefore, you need a really dense the pressure to ignite this reaction. And what's going to happen is that if the white dwarf has a big enough energy, this can happen. Or a star has a very big energy, this can happen. Okay. So yeah, so reverse process doesn't occur. Reverse process doesn't occur because once this reaction happens, neutron will immediately escape. Okay. Sorry, not neutron. Neutrino. Sorry, neutrino. Neutrino. So So if you have this, this somehow whatever. So this is a rough schematic. E minus in the E P plus become P N. Then immediately after that, the neutrino will escape because I mean neutrino does not react to does not react to neutrino does not react to some matter so often. Okay, so neutrino will escape. So the reverse process will be prohibited, and also this process do not occur. Plus nu bar E does not occur. This one does not occur because if you make a rough estimate, already electron degeneracy will already become form Fermi C, and then if this one does not occur because of Fermi statistics of electrons. Okay. So that's what's happening. So this one. So therefore, if the pressure is big enough, so this process, electron and the proton will be paired and become neutron, and the neutrino will escape. And then it becomes the neutrino, instead of the electron pressure, it becomes neutron degeneracy pressure. Okay? And the rough estimate, if you do that rough estimate of the size of the, radius of the neutron star, we can just make the following thing. So since what we need to do is this, you have to make it that this is neutron and this is neutron. Okay? And the neutron and the proton is almost same size. Okay? Neutron, so we can like this way to make a rough estimate of the size of the RC. So therefore, so if you do this computation, essentially we need to multiply RC times ME over MN. Okay? And this is roughly MN squared, and then H bar cube GC, and then 1/2, and this is equal to roughly GMC divided by C squared. Okay? So this is critical mass of independent of ME. So if you just look at compare between this one and this one, I mean MN is almost MP, so therefore you get this one. Okay. And if you look at this one, so many people are familiar with Schwarzschild black hole, and this is roughly almost comparable up to factor of 2 with the order of the Schwarzschild black hole. Okay. So now for neutron star, if you try to study a neutron star, what you need to do is that you need to include the effect of GR. Okay. So here, when you try to get this Chandrasekhar limit, we just use Newton potential, right? So this is Newton potential. We don't include the GR effect. Okay. So for white dwarf, we only use the Newtonian effect for gravitational force. On the other hand, if you try to estimate what's happening in neutron star, you have to include the GR effect because the roughly radius is already like comparable to the Schwarzschild radius. Okay. So therefore, and also you need to include so-called strong forces. Okay, so neutron degeneracy, pressure. To do that, so actually you need to include so-called strong forces. You need to strong force effect. So the neutron star, to understand what's going to happen in neutron star, you need to include both GR and strong forces, which is forces for whatever, nucleon or whatever, gluon, quark, and so on. You really need to include both of them. So therefore, it's very difficult. So even current times, so this neutron star was essentially the first consider is the TOB. So I'm going to Tolman-Oppenheimer-Volkoff. TOB. So 1939. So this is so-called TOB equation. I'm not going to write down all the name because it takes too much time. Tolman-Oppenheimer-Volkoff. But it's very, very, so as I mentioned, so people at that time, it's hard to believe one solar mass can squeeze into 10 kilometers. Okay? So if you have one solar mass, what is the Schwarzschild radius of one solar mass star? Does anybody know? Huh?
3.
Yeah, so roughly like a 2 kilometer. Okay? 2 kilometer is a Schwarzschild radius. So it's really like only 5 times Schwarzschild radius. It's hard to believe at that time the star can just squeeze into such a very small. So this is often called a gravitational radius. Gravitational. So therefore, so it's really comparable with Schwarzschild radius of the actual radius size of the star. So therefore, it's called a compact object. Okay, so then you need to include the GR effect. So let's do that. So to include the GR effect, we need to solve the Einstein equation. So that's the way to go. So let's assume the everything is the ideal situation. Since so the important thing is Einstein equation. So once you have tried to solve Einstein equation, most of the case cannot be solved exactly in the most of the cases, all cases, most cases. So important thing is Einstein equation is really hard to solve. Because the nonlinearity. So nonlinearity means that if you have the one solution and then there's another solution, if you add them up, it can be a solution. That's the linearity. But since Einstein equation is nonlinear, it's really hard to solve. So therefore, exact solution are very precious. The precious, and then require some ideal assumption. So the most of the case, important thing, Einstein equation cannot be solved exactly. So therefore, there is something called the area called numerical relativity. So nowadays, computer has been developed. So the people just solve the Einstein equation numerically to understand what's going on in physically. But in some cases, if you impose a very, very ideal assumption, so one can solve exactly, and then so we will learn from now on the exact solution because there, as I mentioned, it's a very precious because there are very, very rare cases where the Einstein equation can be solved exactly. And then this one, so first done by so-called Schwarzschild. like a few months after the GR, birth of GR. So 1916. So we just assume the static. So metric is independent of the time, and then spherical symmetric. Spherical symmetry, and the vacuum. And then plus, so one is this one. Okay, number one, number two, number three is assumption vacuum. Vacuum equation, vacuum. To understand the neutron star, we need to give up this one. So for neutron start, we need to give up this one. So this is the Schwarzschild so-called black hole. So black hole, nowadays it's called black hole. At that time, people do not believe there's a black hole. But anyway, so for neutron star, sorry, the last time, did I write that one? Sorry. Sorry, my English gets really rusty. Sorry, neutron. Sorry. Okay, I think hopefully anything. Anyway, it's already recorded. It cannot be modified. Neutron star. Star. Assumption fail. So this is the assumption fail. And then you need to use some other assumptions. So for instance, a perfect Floyd and so on. That's what TOB did. So that's what we are going to do. But before going to neutron star, let's first solve the Schwarzschild solution before going down. Okay, so the assumption will give you the following thing. So that and also let's see, 1, 2, 3, and 4 is the dimension is equal to 4. 3 plus 1. 3 plus 1 dimension. And then, I mean, I don't know. I mean, I don't like C, but if you want to do some numerical estimate, you need to keep track of the C. I don't know which one is a good thing. I don't like, personally, I don't want to keep C, but okay, for time being, let's keep C. I mean, usually, what's the body of C? Yeah. So if you ask the GR people, the body of C is 1 actually. And if you are some experimentalist or whatever, whoever astronomer, so C is whatever 3 point blah blah blah. Anyway, it's okay, whichever. Let's first keep this one. And the spherical symmetric, so therefore this becomes H. Spherical symmetric means that the R, FR, and then H of R, dr square plus R square, d theta square plus sine square, theta d phi square. Okay. So this is the assumption. So since the static, so there is no dependence of t. And the spherical symmetric means that the metric depends on only r, radius, okay? Because it's in a rotational invariant, so everything should be depends on r, and then the rest of the spatial coordinate become this 2-sphere. Okay, and we can just call this one is equal to sigma AB dxa dxv. So we can call it like this way. And then try to solve the Einstein equation. Okay. Many people have been already encountered this problem. And then I don't know how much I should mention. Okay, maybe I can just starting from this one. There's a way compute the curvature. Okay, I can show you the compute curvature. So and nowadays the technology has developed. You just now you can just put this metric and just ask Mathematica immediately solve. After the break I can show you. Not now. Or I can send it via WeChat group. I don't know. I mean, if you want, you can play around. Let me send you in the case. For instance, this one. WeChat group. So I just create last night how to solve this one. Let's see, R00 RTT is equal to -1. I mean, it's just a calculation. F prime. It's kind of boring, but one has to do. But it's actually beautiful. So one has to RTT and R is equal to the same thing. This one is the same. And plus H prime R H square is equal to 0. And then RAB. So this capital AB is a really sphere part. The sphere part is in fact equal to, it's kind of like messy, but you have to do that. R square minus F prime 2RFH plus H prime 2RH square and delta AB. Okay. So I just write down this one is the sigma AB del x dxa dxb. Okay. That's the curvature. And you can immediately see that so if you encounter this kind of situation, I mean, it's if you're if you have it's very natural to take a difference between them. So from difference between them will give you the f prime of f plus h prime of h is equal to 0. Okay, so that's what's going to happen. And then if you solve this equation, I mean, it's immediately see that this is the f is equal to h inverse up to some scaling factor of time. Okay? So that is very easy to solve. I mean, if you redefine like constant, integration constant and so on can be absorbed into redefinition of the time and radius. Okay. Time coordinate. So you will get this one. You get this one. And plug this one into here. If you plug this one into here, what you end up with the, okay, this is, let's go number 3. Number 1, number 2 is there. Okay. So number 3, you get the R, F prime is equal to 1. So that's what you get. So if you plug this one into here, you get this equation. Which you can do the using the Mathematica I gave you. That's super easy. So therefore, from here, you get the f of r is equal to h inverse of r, and which is 1 minus rg times r. Okay. So this is the immediate consequence of the static spherical symmetry and with vacuum, okay, with vacuum equation. So, sorry, as I mentioned, so maybe I should mention that the Einstein equation, okay, R mu nu. So now, and then 5, cosmological constant 0. I mean, these equations is really coming from, sorry, I think most of people already understand, but I should emphasize, this is the equation we will encounter, okay? And then, okay, so this means that if you take, this is equivalent to this equation, can you see that? If you take a contraction with respect to g mu nu, then what you get is r minus 2 times r, right? Is equal to 0. Okay? Is it okay? So therefore, Ricci scalar should be 0. That's the immediate consequence of the vacuum equation. Okay? We plug that one into here, r mu nu is also 0. Okay? So therefore, this is the equivalent condition. Okay? Is it okay? So that for Schwarzschild, if you do that, this assumption, then the immediate consequence of the Einstein equation is this one. Okay? Sorry about it. And this one. Okay, and the question is how to determine this the integration constant. Okay? So if you solve this one, you plug this one into here. This is the integration constant, Rg, and how to determine this Rg. So we're not gonna, I don't want to erase this one, maybe. Okay, so to find Rg, so we'll somehow make an estimate. So, question? So what's going to happen? So there's something happen in Rg. So if you plug this one into here, R equal to Rg is the apparent singularity. So it's got apparent singularity. So that's why people just are skeptical about this solution. If you plug this one into here, when R is equal to Rg, so F will vanish and H inverse will become infinity. So there's something strange happening. So that's why. But the question is, if the Rg, the R is way bigger, Rg, you can take the Newtonian approximation. So let's do that. So what's going to happen? Newtonian approximation. Okay. So far away from this. So to do the Newtonian approximation, we will see the following thing. So it's really far from here, far from the Rg. So what's going to happen is as follows. So number A is the G mu nu is almost flat. A mu nu plus H mu nu. And the absolute value of this one is less than 1. Okay? And then number B, H mu nu is the independent. This is already assumption in the Schwarzschild black hole. And C is G0I, H0I is equal to 0. And D is the velocity of particle in this, how to say, the region. So this is a Newtonian approximation. I mean, this is much more general than the simply looking at the Schwarzschild. So, but Newtonian approximation, this is the approximation. We assume this. Okay. Okay, so then what you get is that the following. So if you look at geodesic equation, when you, in the Newtonian approximation, x dot alpha, x dot beta is equal to 0. But if you do the Newtonian approximation, for instance, number D will tell you that this one is something like this one. Spatial part is equal to minus gamma I alpha beta x dot alpha x dot beta. And then we can assume that this one is really, I mean, the particle is essentially like a static rest frame. So therefore, this one only matter in the time component. And time component, and then this is roughly I00 c square. Okay, c square. Okay, and then if you do the following assumption, this assumption, what you get is as follows. This is indeed equal to -1/2 del I H00. So this guy. So we assume the H is depends on some coordinate x, the spatial coordinate x, okay, spatial coordinate x, and we assume that the G, like a time space component will vanish. Okay, then because I mean we just do this like how to say, the slight fluctuation from the flat metric. So then if you plug this one, this is true. And then, so therefore, if you compare with the Newton equation, this is equal to, Newton equation is, as you know, this is I, and then minus del phi. So this is the gravitational potential, okay? Gravitational potential, if you take a derivative, you get the, how to say, acceleration. Okay, so this is a Newton equation. You can compare between these two. Okay, so then this will mean that the phi is equal to c squared over 2 and h00. Is it okay? Fine. So therefore, if you use this one, so if you're far from the radius of this one, so that you can determine, so this h00 is in fact this guy, right? Where's the color choke? So this is the is h00 because the we assume that the f of t, no f of r, dt square. Sorry, maybe I still keep c, and then f of r inverse the what was that? R square plus dot dot dot. People usually let that d omega to like this way, or maybe square, r square like this way. So therefore, we'll f of r and the deviation from 1 is in fact h00. Okay. Therefore, if it really go too far away, it should give you the Newtonian potential. Okay. So therefore, if you compare with the this Newtonian potential, we can just conclude that this one is equal to. So this one, so the so minus Rg of r is in fact equal to minus 1 plus 2 times phi over c squared. Okay. It should be, so the h00 is the, yeah, h0 should be 2 over c squared. And so therefore, and if you compare between these two, phi should, Rg should be the 2 times g m c squared. Okay, c squared. Okay. Do you agree with that? Do you agree with that? I personally don't want to erase this one, so I just let me erase around here. Okay, so if you plug this one into here, so the 2gm c squared r is equal to minus 2 phi over c squared. So therefore, phi is equal to gm over r minus. So that's how the you can determine the integral coefficient Rg. Therefore, you get this Newtonian potential. Let's do a bit. Let's do some exercise for how to get. I think most of people already knew, but let's do some. Let's a little bit study what it means by Newtonian approximation for the Einstein equation. So the Einstein equation is the R mu nu minus 1/2 G mu nu R is equal to 8 pi G. Yeah, I personally don't like G and C, but let's for time being, let's keep it. Later I will set the 1 later. But this one is equivalent to now the cosmological constant is equal to 0. And then this one is equivalent to 8 pi G. If you take a trace and subtract C to the 4 T mu nu minus 1/2 G mu nu. Okay. So this is the case. And if you take non-relativistic limit, non-relativistic or Newtonian limit, whichever you call it, non-relativistic limit, and then we just only care about our 0,0 component, and the 8 pi G is equal to C to the 4 T00 minus 1/2 G00 and T. Okay, so this is the 0,0 component. Non-relative limit means that G00 is roughly minus 1, and then T is roughly the all time component important because that's why I just keep C. In fact, that's the reason so far I keep C, because C is bigger than Euler scale of time, Euler scale of speed. For instance, even if you run, you cannot beat C, even though it's 1. Anyway, so you can just this assumption and plug into here. So if you plug this into here, what you get is in fact this is equal to 4 pi G over C to this C square rho. Okay, C square rho. Rho is the how to say energy density. So rho is the energy density. This is the energy density or mass density, whatever, in the non-relativistic or mass density, or whichever. Okay. I think since we take the I think mass density is more precise because we multiply C squared. Okay. And then we just take a look at the what's R00 in this Newtonian approximation. So R00 in Newtonian approximation is in fact gamma I0, and this is equal to 1/2 negative del square H00. Okay. Okay, and plug this one into here, and then compare between the two, and this will give you nabla square phi is equal to 4 pi G rho. Okay. And in fact, that's how, if you compare this one and the non-relativistic limit, that's how Einstein determined this coefficient. So this coefficient is determined by comparing this Poisson equation of Newtonian gravity. Okay. So that's how Einstein originally, how to say, determined the coefficient. So Einstein Hilbert action. So I didn't include it because I mean it's not important theoretically. I mean essentially, this is the action time constant. And I missed this constant when I if you look at the video or you remember, I missed a constant because I'm the, how to say? Anyway, I'm stupid. So the constant, this constant will determine this guy, this coefficient, okay? And this coefficient is, for me, it's not important, but if you take the Newton transformation, this should be the constant. That should be the constant. So that's the how Einstein originally determined the CQ 16 5G. So this is the constant. So that's the Newton approximation of the Einstein equation. So you can get the Boston equation from the Einstein equation. Let's move on. Okay. The reason why I keep this one is that so I just want to do the following thing. So this is Schwarzschild workflow. I'm going to discuss more in detail, but before going to detail of the Schwarzschild workflow, let's talk about a bit about the neutron star. That's why I just keep this one. So neutron star, as I mentioned, so there is something, there's a star. So you have to make some, it's not vacuum. So the space-time is not simply vacuum. So you have to make assumption. What kind of like, did I erase? No. So if it is not vacuum, there is something on right-hand side of the Einstein equation. Okay, there's something. And then TOB assumes the following is a perfect fluid, so, but you can just assume that the neutron star, which is roughly 10 kilometer, radius is 10 kilometer, and there is something inside, which is neutron mostly, and then whatever, lots of things going on, superfluid and so on. Of course, the center is denser than the the surface. That's true, but let's make it as a theoretical physicist, make an assumption. So the perfect fluid. Perfect fluid. Okay, perfect fluid. Let's the assumption. So this perfect fluid is indeed almost definition is the rho c squared plus p. Yeah, again I keep c p pressure, and rho is energy density, u nu, p g mu nu. Okay. This is the static mass density. Okay, so I think here mass density is more precise. I should mention static actually. And then P is the pressure. The pressure of the perfect fluid, and U is the how to say four vector. I don't know, four vector of the perfect fluid. Okay. Rest frame. So this one rest frame. This is equal to rho p p. Rho c squared, maybe c squared pp. So this rest frame. If you take a rest frame of essentially u is maybe some sign difference is the occurred, maybe no, it's okay. So u mu is something like a 1 0 0 0. That's a rest frame. And then you can just take the static space-time, yeah, like this. And then it takes the following. So this is almost definition of a perfect fluid. So the perfect fluid, the stress energy tensor, it takes the following form. Okay, and then we again to make an assumption. Can I erase? Okay, maybe I will erase here. So make assumption that the static, neutron star is the static and then spherical symmetric. And yeah, so this means non-rotational. Non-rotational. Spherical symmetric, and then it's plus perfect fluid, and of course the lambda equal to 0. For time being, lambda is always 0. So for time being, I don't consider the cosmological constant. So then the computation is almost similar to what we did for Schwarzschild. Okay, so metric part is the same. Okay. Metric part is the same. So we start with the metric minus f of r square d c dt square plus what was that h of r square dr square plus d omega 2 square. Sorry, maybe I should put the r square is equal to ds square. Okay, so that's the assumption. Start with this one and try to solve the Einstein equation. Solve the Einstein equation, and what you get is this one. So we already compute our part, and then we can use the so therefore 8 pi. So the 8 pi g C04s. And T00 is equal to 8 pi r g c square rho c square, and which is equal to G00 0. And then if you just do the computation, so this is the Einstein equation, you have the h square minus 1 h prime plus r minus 2 1 minus h minus 1. Okay. So that's what you get. And then here we already compute this one is in fact r00 minus 1/2 g00 r. Okay. Okay. Now it's right hand side of Einstein equation is non-trivial. Okay. It's not vacuum. So therefore, Rich tensor not necessarily vanish. Okay. Rich tensor is not necessarily 0. So that for if you assume the vacuum. So Rich tensor is 0. We already showed that. But for non-trivial stress energy tensor, it's no longer true. Okay. And then you can do the same thing. 8 pi g divided by C04 T11. I mean this one. I mean it just use the computation of this. Nowadays it's super easy to do because I mean we can have the nice computer and so on. But before then it's to the fourth. Yeah, I don't like this G and C4, but let's keep it for time being. It's equal to G11, and this is equal to RFH inverse F prime minus R minus 2, 1 minus H inverse. And then we have some special part. Spatial part, the same thing. So T22, the same thing. And this one is same thing. I don't like this constant, so I will omit P, and this is G whatever, 2, 2. And this is equal to, it's complicated. So I will erase this one. Okay, and this is equal to 1/2. It's FH minus 1/2 dr, and then FH 1/2 minus 1/2 F prime. Hey, plus, it's complicated, RFH inverse F prime minus 1/2 R H squared. I mean, you can just, if you use Mathematica, it's easy, but writing blackboard kind of takes time, okay? So that's the case. Hey, you need to solve this equation. And who solved, so the person who solved this first is in fact Tolman-Oppenheimer-Volkoff. And then they assumed the following thing. F of R, we can just write down like a minus is e to the 2 phi. And then they assume that the inspired by the Schwarzschild, h of R is equal to 1 minus 2gm of R or c squared R. So the spatial part, radius part is really inspired by Schwarzschild, because we already made an estimate that the the neutron star is roughly the size of a Schwarzschild black hole up to some factor. So therefore, the spatial part can be just a spatial or radius part of the metric can be written like a Schwarzschild metric. But the important thing is that the mass is really depends on the radius, because I mean the Schwarzschild it's a vacuum equation, so therefore it's independent of the radius. Mass is independent of radius, but here we have a star, and then the star has a size, so therefore mass should depend on the radius r. Okay, and then plug this one into here, and solve the equation. So that's what the TOB did. So now I can erase. So if you plug this one into and solve it, and then what you get is as follows. The first equation is very natural. It's 4 pi r square rho c square. Rho c square. It's very natural. The dependence of radius of the mass is given by the static mass energy mass density. It's very natural. And then the immediate consequence of this equation, this one is also very similar, easy. I mean, you just plug this one into here and look at the first two equations. What you get is as follows: minus 1. I'm not going to derive everything. Actually, this is the homework you have to solve. I think it's a good exercise. I don't know. I promise the homework was not so difficult, but I think this level is okay for you guys. Anyways, there are lots of literature. As I mentioned, this derived in many books and so on. I'm not going to. But third equation is very non-trivial. Plus b. 1 plus 4 pi r cube p divided by mc square. So the third equation is very non-trivial. 2gm divided by c square r inverse. So the 1, 2, 3. So this is the most difficult. The most difficult. but you can get this one, and this is called TOB equation. So if you solve this, to solve these three equations, so we need to be careful, okay? We need to be careful that we need to solve okay, yes. Here, so to solve this equation, we need to specify P of rho. So as you can easily see, let's see. Yeah. So here, if you compare 1 and 3, so if you look at the 1 and 3, 1 and 3, if you look at the 1 and 3, okay? 1 and 3, what are the unknown variables? So one unknown variable is M and the rho, these are unknown. And also P, okay? And the M is unknown, rho and P, okay? P and M and M, okay? These are unknown variables, okay? So rho and, if you look at the 1 and 3, P, rho, M are the unknown variable. However, you have only 2 equations, okay? So 3 unknown for 2 equations. So that's not, you cannot solve it. So therefore, we need a so-called P of rho. How the pressure depends on the static mass density. So this is the state equation of the neutron star. State equation neutron star. One has to give some how does the pressure and then mass density are correlated inside a neutron star. Okay, so you have to make some assumptions on, okay? And you have to make assumptions. And many people did that. First assumption, TOB gives some very how to say, naive assumption for P of rho, and then TOB obtained roughly the maximum mass of the how to say, neutron star. Max is like this way, maximum mass. So that's the first TOB in like 1939. They assume very simple assumption of P of rho function, and they obtain this one. They don't include any assumption of strong force and so on. So they obtain this one, which is less than the Chandrasekhar limit. Okay, so that's why the people are kind of skeptical of this result, and also, but if you introduce strong forces and so on, some the latest estimate is roughly n max of neutron star is indeed around the 2.2 to 2.9 solar mass. If you solve, if you make estimate of P of rho and solve this equation, and then roughly the maximum the neutron star is around here. Okay. And then so 2022, there's observation. So far, the P, I don't know. This is the name of the neutron star, J09520607, and the mass is 2.35 plus minus 0.17 solar mass. So this is the biggest, heaviest neutron star observed so far. Okay, so therefore estimates is roughly okay by solving this P of rho. But still, there are lots of here it's we don't include the effect of the angular momentum. Okay, that's the one thing. Most of the neutron star has almost all. I think all the observational neutron stars have the angular momentum. So therefore, this estimate is the really rough estimate. So it's not the precise estimate. So you have to include the effect of the angular momentum, which we are going to do by using the cometric and so on. We studied cometric. But anyway, so this 1996 paper is in fact include all this angular momentum and so on. But anyway, but estimate is roughly okay. But still, for neutron star, you have to include the effect of GR and also strong forces, and many things are still unknown. For instance, this P of rho is still how the precise equation and P of rho and so on. So here also we assume the perfect fluid, but the actual neutron star is not perfect fluid. But there's something going on inside. People all widely believed, it is widely believed there is some superfluid inside a neutron star and so on, which is away from my expert. But maybe if you are interested, maybe you can ask Cosimo or somebody else. Anyway, so those are the physics of neutron star observation is still largely unknown. So there are lots of things and lots of thing going on, and then if you're interested, you can just do the research and tell me what's going on, because I'm unfamiliar with it. Okay, let's take a break.
Tolman calculate the maximum of neutron star is 0.7. Right?
Yeah.
What kind of assumptions they made for equation of state?
So P of rho.
To calculate this.
I think it's just an ordinary, I don't know. To be honest, I don't know P of rho.
Okay, and then they made an assumption for this equation of state, and then he solved this equation 1, 3, and this together and get this result, right?
Yes.
But how did they do that? Because it's not possible to solve analytically, right? They solve it numerically, or is it possible?
Yeah. I think numerically, because the P of rho is the kind of it's hard to solve.
In that time, in 1939, is it possible to solve numerically?
I think that's why. I think P of rho it is a really rough up assumption that they can do the computation by hand. That's the reason why it's 0.0.
And they solve these three equations numerically and find that result 0.7. But and after including rotation and strong force, this one is issued in 1996, right?
Yeah. So this one is really numerical, and this somehow make assumption of P of rho by using a strong forces analysis.
How can strong forces affect? Can you give us all evidence?
I don't know. Oh, good, good, good. Okay, it's working. 이건 모니터? 디스플레이. Why is it not working? Just now it's working. It was working, right? do you know how to use this to make a laptop visible? Can you help somebody? Oh, it's working. But somehow it's a... Okay, maybe it's okay. Okay, shall we resume? So here's the one I sent a Mathematica. So once you encode like this is a metric of the matrix, and then we can just easily compute the Christopher symbol. This field means 0, and the Ricci tensor. No, Riemann tensor, Riemann Christopher tensor, this is Ricci tensor, and so on. And you can just also compute a Ricci scalar. Yeah. And also, if you use the correct metric for Schwarzschild, this is a correct metric for Schwarzschild, one can compute the Riemannian tensor like this way. And as we know, so Ricci will vanish. So therefore, R is always 0. Okay, R is always 0. And the important thing is that if you compute the quantity like RAB, RABCD, so this is the quantity I computed in here. Okay, so it's proportional to 1 over r to the 6th. Okay, as you can easily see. So this is the quantity I computed, and then the rest is depends on like r squared and so on. But there is some constant term appear here, so therefore which this computation means that there is something curvature is singular at r equals 0. But no, r is equal to r, whatever, Schwarzschild radius, okay? And so on. I mean, you can easily create this kind of like code and compute the metric and so on. So it's nowadays super easy. So that's I just wanted to show. Anyway, so that's I wanted to show. Okay. I think even if I stop this one, shock. Good. And then, so you can play around by using Mathematica to solve the Einstein equation. Okay, and now let's move back to the Schwarzschild black hole. So as I mentioned, many times the concept of black hole is a big idea. It took nearly half century for human beings to accept the idea of black hole, even though the Schwarzschild solution is already known. A few months after the birth of the GR, Einstein's paper. So as I mentioned, so that Chandrasekhar limit is around 1.4. solar mass. And then neutron is, as I mentioned, around the 2.2 to 2.9 solar mass. And the question is, what's going to happen after if the mass is bigger than that one. So then it is now believed that if the gravitational force wins against the neutron degeneracy pressure, then literally gravitational collapse will occur, and then form the black hole. So that's the widely believed. And then once you do this contraction, you will get the so-called supernova. Again, it's type 1A supernova, which I'm not so familiar with. But in any case, if the mass of the Chandrasekhar limit or this neutral degeneracy mass, if it is above then they will form the black hole. So now it's believed like this way, and then so that's why the black hole solution is very important. And then let's see what's the causal structure of the black hole. Okay, and as I mentioned, so the ds square is equal to -1 minus 2g. Like this way. So this is a Schwarzschild black hole metric, and then there's apparent, so the R equal to RG, there is some apparent singularity. But if you compute this R cross R, and then it's proportional 1 over R to 6. So the only genuine singularity is R equal to 0. But as you can easily see, so important thing is that the R equal to RG is the apparent singularity. So that's just apparent, not genuine. But not genuine singularity. But the important thing is that the R equal to 0 is the true singularity, genuine singularity, true singularity. Because of this analysis, And also, here important thing is that the distance becomes f of R is negative when R is less than RG. It's negative less than R with RG. So therefore, somehow this part behave like a spatial metric. And in fact, this become negative. And so therefore, this behave like a time like a metric. Okay, let's a bit more analyze. So therefore, so to analyze the causal structure, so let's analyze the causal structure of the Schwarzschild black hole. To do that, let's look at only focus on this time and the radius component. F of R equal to 0. So let's look at this is the radial light way. Radial light A, and solve it. So then if you solve this one, the dt dr square is equal to 1 over c r minus g. And so this is the differential equation. One can easily solve this one. Okay, so you just do that. dr is bring it to denominator, and if r is bring it to the right hand side, you get this one. And take a square root and do the integration. Square root and integration, what you get is as follows. Ct is equal to plus minus r square, and then plus constant, and this r star is indeed given by, r star is given by, maybe I should write down, r star is given by as follows, is equal to r plus rg, and then log r rg minus 1. Okay, that's the r star, but it's here. Okay. So these are the equations of the trajectory of light ray. Should I erase or I should go here? So these are trajectory of light ray, and each trajectory is leveled by integration constant. Okay. And then we can just furthermore introduce the change of variable like that, the following. So if you do that, we can do this following change of variable. So u and is equal to ct minus r star, and v is equal to ct plus r star. Okay, so that's the. Okay, then the metric become like this way. Metrics become 1 minus rg over r du and dv. That's is it okay? Should I show the computation or not? I think it's okay, right? So this can. Anyway, so du is equal to cdt minus dr star. Dr star is dr plus what was that? 1 minus rg inverse times dr, right? Times rg. Okay, is it okay?
No, without RG.
Huh?
Dimensions should be just R. RG cancels.
Yeah, so RG cancel, right? RG minus.
No, she was differentiated.
Oh, yeah, you're right. Okay, good. Okay, like this way. So therefore, and then dv is equal to cdt plus this guy, and if you multiply it together and multiply it, and you get this upstairs. This one. Is it okay? Is it? You can see that? I hope you can see that. And this one is equal to the following. So minus rg of r, and then what was that? E to the b minus u over 2r times e to the minus r over rg times du dv. Okay, so that's the case. So let's look at what's going to happen when r is equal to rg. Okay. When r equal to rg, here r star become infinity. Okay, r star become infinity, right? So if you plug this one minus 1, this become infinity. So therefore, u and v becomes the minus infinity and plus infinity. Is it okay? However, this part become a 0. So therefore, this look like a coordinate singularity when r equal to rg. Okay. So to avoid this coordinate singularity, we further define the following thing. U is equal to minus e to the u over 2rg, and capital V is equal to e to the small v over 2rg, and write down the metric. write down the metric. Yeah, sorry. When r equal to rg, this is minus infinity. Sorry, minus of infinity. So therefore, u become infinity, v goes to infinity, but this becomes 0. So this becomes 0. This becomes 0. So the coordinate singularity. And to avoid this coordinate singularity, so we just make a change of variable and write down the metric again. Then this one become like this way: rg and cube, and then r e to the minus r over rg, capital du and dv. Okay. Now it's a regular at r is equal to rg, as you can easily see from here. Okay, is it okay? If you plug r equal to rg, it's totally fine. It just look like flat metric plus there's some component factor. Okay, plus component factor, which I'm going to explain about the in terms of Penrose diagram later. Okay, so that's the case. And then here, as I mentioned, so when u is equal to constant, some constant is light ray, as I mentioned. So u and then so the u and v are constant is really right ray. So that's why that's how we how to say introduce u and v. So capital U and capital V are constant again is the capital U and capital V constant is again light ray. And to make this kind of like a space-time look like variable, we introduce the following thing. Do I make a mistake? I think I told you wrong. Yeah. I think I told you wrong. I think it's okay. Sorry, I got confused. Anyway, let's move on. So I think it's okay. So then to make the new coordinate, so the t of x, t is equal to u plus b over 2. If you want to include c, it's okay. C. And x is equal to u minus b over 2. Okay. If you introduce like this way, what you get is as follows. So if you introduce this one, the metric is become the following: ds squared is equal to 4rg cube over r e to the minus r over rg, and then here you have the minus minus c squared dt squared plus dx squared plus dr squared d omega d squared. Okay, so this is a metric we will get. So this really look like the flat metric, really, with some. This is called component factor. So it depends on radius r. Okay. So then we can just write down how the coastal structure look like. So if you look at the relation between r and x and t, in fact, r over rg minus 1 is equal times e to the r over rg is equal to x squared minus ct squared. And then ct over rg is indeed given by log of ct plus x divided by x minus ct, and which is the sum inverse of tanh of the ct over x. So that's a change of variable we will make. We just need to you just need to keep track of the definition of t and r, and then u and capital U and q and v, and you get this one. Okay, from here one can conclude that when r equal to rg is given by ct squared is equal to x squared. Okay, ct squared equal to x squared. Okay, so somehow my okay, I need to change the graph. Okay, and then r equal to 0 is given by so given by ct square is equal to x square. And the r equal to 0 is given by just plug this one into here and then solve it. And this one is equal to x square minus c square t square is equal to -1. Okay, and then r is equal to 0 is in fact is given by like this. Okay, so that's the case. Okay. Is it okay? And t is constant. T is constant means ct over x is constant. Is it okay? Small t is constant. Is the ct over x is constant. Fine. So therefore, let's look at how it looks like. So again, so this is called Kruskal coordinate. So this where's the metric? Where did I write the metric? So this is called Kruskal coordinate. This is called Kruskal coordinate. I forgot the name of the other person. Sorry. I print out the old name. So what was it? Anyway, in my lecture notes, it's written correct name. I forgot the name. Sorry about it. Kruskal is I don't know. Coordinate. Sorry about it. Let's see. Yeah. Anyway, so those the capital T, capital X, and then this. If you use this one, this is called Kruskal coordinate. This appeared around the 1960s. Okay. So let's look at the causal structure. So when r equal to 0 case, you have this. Okay, so you have this u and v. This is u and v. I forgot which one is u. This should be u, maybe. This should be v. And then u is good. Anyway, so this is actually in fact equal to r equal to. So c square is equal to t square and the x square. And then, I don't know, I mean, maybe this orange is better. And xy, t and x, so this is ct and this is x. So the horizontal axis is capital X, the vertical axis is the capital T, like this way. Sorry, my lecture note is somehow strange. The variable is somehow strange. And then, as I mentioned, when t is equal to constant, when t is called constant, ct over x is constant, which means that all the t is called constant is something like this kind of line. So this is t equal to constant, and this is t equal to constant. Okay. Is that okay? So these small t is constant line. On the other hand, r is equal to constant, you have to solve this equation. So when r is a constant, left hand side is constant, but x squared minus ct squared is, so which means x squared minus ct squared is equal to constant. So therefore, the constant is, r equal to constant is something like this one. Yeah. And so on. So these are r is equal to constant. Okay, so those are r equal to constant part. Okay, is it okay so far? And then r equal to rg is in fact the ct square is equal to x squared, which means that the really 45 degree of this orange line. Okay. Okay, so these orange lines is really r equal to rg. Okay, rg. Okay, and r equal to 0. R equal to 0 is x squared minus c squared t squared is equal to -1. Okay, so therefore t squared must win versus x squared. Do you understand what I mean? So right hand side has to be negative. So therefore CT has to be bigger than x if you assume that. So therefore it has to be in this region. Okay, and then the line should be something like this way. So this is r equal to 0. Okay, and then here, since as I mentioned, the curvature goes to infinity, so it's a true singularity. Okay, true singularity, r equal to 0. Fine. And then if you write down the trajectory of particle, maybe I should use some other color, but I cannot find some other color. So everything has to be time-like, the time-like. So therefore, it becomes something like this way. So I don't know, a minute. Sorry. Timeline like this. Okay. So inside the timeline, then all the cone, so the light cone, it becomes like this way each time, like this way. So these are light cone, become like this way. So always this light direction is 45 degree. Okay, 45 degree is the. Therefore, if you look at here, so it's again, so the light cone become like this way. So if you hit this orange line, so light cone, one of the light cone is really tangential to this orange line. Okay. So therefore, if you look at the causal structure at this point, everything inside of this region. Okay, so in the
shouldn't the axis of the cone be oriented along the t equals constant lines?
Oh, why is that?
The line cones. Why are you drawing them like vertically?
Which one? Small t is constant, right?
Smaller, it should be small.
This is small t.
Yeah.
It's constant like this way. Is that what you mean? No, what's the question?
The orientation of the light cones. I don't quite understand why they don't always with the axis along the capital V
Axis of capital V and capital U, you mean? Because I mean, we define the light ray is always small u, small b is constant, right? So therefore, capital U and capital V is constant. So it always needs to be 45 degree.
Okay.
Yeah. So therefore, this is okay. Okay. And unfortunately, I'm running out of the color, so maybe we can call this one is number 1, and then number 2, and number 3, and then number 4, like this one. Okay. So as I mentioned, so if you only look at this Kruskal coordinate, the Kruskal coordinate, here it's just flat metric. Capital T and the capital X are flat metric. Okay. So therefore, capital T and the capital X can go to the -1 infinity to +1 infinity. One can consider, but however, there is some constraint if you compare with R. If you R is so we assume the R is always non-negative. So therefore, this is the really hits the how to say. I don't know. I wouldn't say. I mean, there's some kind of boundary, of space-time. Okay, some kind of boundary because the R cannot be negative. Okay, so therefore you cannot go above. Okay, the similar thing happens. So, but you can extend analytical continued since this metric, capital T and capital X, you can just assume it can extend any values unless you hit some constraint in the original variable. And then we can just also see the following thing. So you can just, here we just, here is just go to the, so this is the R goes to infinity. R goes to infinity because I mean the R is constant is like this way, and if you go to the here is just the R goes to infinity. Okay, so this is the place you just you consider you live in. The R goes to this is Minkowski. It's spatial infinity. However, you can just consider the analytical part 3. Okay, so everything. So as I mentioned, so here, so if you hit this light, how to say, this R equal to RG gravitational radius, all the light cone is just move toward number 2. So therefore, you cannot escape. But course abstraction mentioned that the number 2, if you once enter this how to say gravitational radius, everything you cannot escape from number 2. It's just everything drawn to the R equal to 0. R equal to 0. So therefore, this is the really singularity. And same thing, if you do the analytical continuum, same thing happening here. So if you have the number 3 analytical continuum, you have that here is equal to what's the curve of this one? It should be what's that? What's the curve should be? Yeah, it's the same curve. So CT is bigger than the X, right? So therefore, this also satisfies this one, right? This equation. Okay. So this curve is also satisfy this equation, and because I mean you have 2 copy of this the how to say parabola or what is it called? I don't remember. Hyperboloid. Hyperboloid. So therefore. So this is also singularity. Singularity, you encounter. But here is again causal structure, everything coming from here. I don't know how to draw. Everything coming from here is always something like go out of the, I think I should write down like this way maybe. Go out of the number 3 region, okay? So often people call this one black hole singularity. So remember, black hole is not the, when you say black hole, the region 2 is called black hole. Okay? Region 2 is called black hole, but this black hole doesn't mean not necessarily means only the singular point, R equal to 0. Black hole means region 2, so including all the horizon, space-time horizon, inside the event horizon. Okay, so R equal to RG is called event horizon. So region 2 is called black hole. So not, I mean, when you say people sometimes confuse that the black hole means the singularity, R equal to 0. That's not true. So all the area inside the event horizon is called black hole. So inside a black hole, there's some singularity. But here, everything's go, how to say, move out of the region. So therefore, this is called white hole sometimes. Here again, so the reason why we have a white hole is that it's not physical. We assume the static, spherical symmetric, and then bunch of assumptions we solve, and then do the how to say, change a variable and another continuation, we will get this diagram. Okay, but in the case of reality, what's going to happen is the following. What's going to happen is that I'm going to almost writing down the. What's going to happen is that this is T, small t or Ct and R. So what's going to happen is that something like this one. So this is R. So there's a star is collapsing, as I mentioned. If the certain amount of the the mass or Chandrasekhar limit or this neutron degeneracy pressure starts losing the gravitational collapse, the star will collapse. So this is time direction, and then the R direction is here, and there is some inside a star. Okay, and if you have the this corruption, there is some so-called R equal to RG will show up. Okay, R equal to RG will show up. And then, as I mentioned, so here, so if you hit so it's R equal to, so event horizon. Because this the Kruskal cone is always look inside. Look inside of the black hole, inside a black hole. So this region is called black hole. Okay, not only singularity. So this region, all the region is called a black hole. So be careful. Even like a physics students make a mistake. So all the region is called black hole, not only singularity. So this is called black hole. So therefore, the spatial infinity is here, and this is the number 2 region. Okay. So therefore, what the physical process happening is that there is some everything starts from the star and then burning out all the energy, and it starts collapsing due to the gravitational attraction after the supernova, and you will get this state. So therefore, what we are in reality, what we look at, we can see is only number 1 and number 2 region. Okay, physically we can see only number 1, number 2 region, and however, so if you solve this Einstein equation by imposing static, spherical symmetric, and so on, and with vacuum equation, since there is no star from the beginning, so we assume that the vacuum, we solve the vacuum Einstein equation. So therefore, from the beginning, so initial condition is a vacuum. Okay, so therefore one can analytically continue number 1 to number 3, but it doesn't happen in the reality. Okay, so that's widely believed. And then so once you create a white hole, and then white hole, one can just consider the following process. So we can again, so if you have some particle just move from here, or maybe move to the other direction, like this way. So when capital X can be negative, right? Capital X can be negative. This is positive direction and negative direction. Okay. So one can analytically continue the solution of the Schwarzschild into capital X goes to infinity. Okay, and then so 1 and 4 are called the 1 and 4 are called separate universe. So 1 and 4 are separate. So 1 and 4 are separate. Yeah. Disconnect universe. Or separate or parallel, separate and parallel the universe. So it's disconnected. It's causally disconnected. 1 and 4, right? So there's no way to make a communication between 1 and 4 unless you just only use some classical mechanics. Okay. There is a lot of work using entangled entropy and so on, but I'm not going to go into detail how people communicate 1 and 4 and so on. But I'm not going to go into detail. Any question at this moment? So one quick comment about this. So what if M? So I already erased the Schwarzschild matrix, so I cannot. Anyway, so Schwarzschild metric. So essentially, what we have is the f of x 1 minus rg minus over r dt squared plus the same thing dr squared plus dot 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 ds squared is equal to this. Okay. And rg is equal to whatever 2gm over c squared. I don't know. So anyway, so here we usually assume m is always mass is always positive, and in the reality that this is the case. But if you assume if m is negative, this f of t r is equal to 1 minus rg of r is always positive. Okay, always positive. Okay. If m is negative, the rg is negative, so therefore this quantity is always positive when r is positive. So therefore you never encounter fr is equal to 0. So as I mentioned, so this event horizon is fr is equal to 0, right? Event horizon appear in fr is equal to 0. Okay. So therefore it's always no event horizon. But we know that the curvature R whatever ABCD, R ABCD is proportional to 1 over r to the 6. So there is something singularity happen when small r equal to 0. Okay. Even though there is no horizon, there is some singularity happen at the space-time. So this is called. In this case, it's this will lead you to so-called next singularity. So r equal to 0, there is singularity, but there is no event horizon. Okay, so that's called event next singularity, and it's widely believed there is, in reality, there is no such a thing. So it's called weak or whatever, weak or strong. There is a cosmic censorship conjecture. Yeah, censorship conjecture by Penrose. So this is I don't know 1960 something, the late 69 or something, or 19, like almost close to 1970. So the Penrose made some conjecture, some conjecture about the cosmic censorship conjecture, and it actually this conjecture will exclude this next singularity. But that's very natural because I mean we want the energy to be positive, right? Positive energy theorem and so on. Anyway, so we will talk about positive energy theorem later, but it's very natural to exclude this next singularity in reality. Any question at this moment? If not, shall we talk about the Penrose diagram? So since we have this diagram, let's talk about Penrose diagram. Okay, so Penrose diagram. Penrose Carter diagram. Or diagram. Or sometimes it's called conformal diagram, whatever. Okay, sometimes. So what we are going to do is that I'm so stupid. I erase. So the Kruskal coordinate. If you use Kruskal coordinate, you have some function, whatever g of r, and then minus ctx plus the x squared plus whatever r squared, the omega 2 squared, and so on. So that's what we encounter for the Schwarzschild metric. And here, as I mentioned, so here is a flat coordinate, right? Flat coordinate up to some factor. Okay. So therefore, I mean, either thing, and then if you look at the how to say it, light ray, it always 45 degree. Okay, it was 45 degree. So therefore, if you just forget about this one, if you forget about this conform factor, you can draw the diagram very nicely. So if you appropriately normalize this factor appropriately, that you can see causal structure of spacetime very, very nicely. Okay? So that's the idea. So it's a very, very simple idea. But the caution needs to be paid because so you just change the metric like this way to the ds square. So this is the whatever physical metric. This is physical metric. So ds is equal to omega square of x ds square. So you just scale by this is conformal factor, but caution needs to be paid because this metric, almost always not necessarily, satisfy Einstein equation. So this metric, if you multiply conformal factor, it's almost always it's not the solution of Einstein equation, even though ds is a solution of the Einstein equation. So to the meaning of this multiply conformal factor is to see the causal structure in a simpler way. But you have to pay the cost. You have to pay the cost that it's no longer obey the Einstein equation. Okay? Yeah, that's a cost that you have to pay. But we want to see the causal structure of spacetime more simpler way, or like a compact way. I would say compact way. Compact way. Okay, let's do that. Let's see. Let's do the simple exercise. I want to keep this one. So if I try to erase this border, but please remind me, do not erase. I want to keep this one. Most likely I cannot go to Schwarzschild, so it's okay maybe. So let's example the Minkowski space. Okay. So we want to see the causal structure. So Minkowski space is something like ds square is minus dt square. Sorry, I already erased the c now. It's, I think, okay to erase c now. And the capital U is the tangent inverse of t minus r. And the capital B is equal to tangent inverse of t plus r. Okay. So remember, so this is theta and the function of tangent, and then this is equal to what was that? Pi over 2 and minus pi over 2. I don't remember. What was that? Is it okay? Sorry, my it should be okay, right? And then the function is something like this one, right? Is it okay? Pi over 2. It's okay, right? So therefore, so here the function range is minus infinity to infinity. Okay. But you can repackage everything to the minus pi over 2 to pi over 2 if you use the arctangent or tangent inverse. So you just repackage. I mean, space-time is minus infinity, plus infinity. But we want to compactly repackage space-time. You can use tangent inverse. So that's a simple idea. And if you write down this one, so the metric becomes like this way. ds squared is equal to something like minus 4 du dB plus sinh b minus u d omega 2 square 2 times this conformal factor cos u cos b. Okay, and the reason why I use the t minus r and t plus r, the variable is I want to keep the Kosa structure. Okay, well t equal to r is the sum equal to 0 or constant. This u and b want to be constant. Okay, that's why I just use this ratio. Okay. So then if you use this one, the metric becomes like this one. Okay, so here it's of course it's no longer the Thank you so much. Okay. Oh, good. Thank you. Students are very still like careful than I am. I'm a 粗心大意。Okay, so then let's focus on the following thing. So if you just multiply, the factor d as cos u cos b square and this s square. So the original metric is like this way. If you after change about, but you can multiply this is the denominator part. Sorry, I think I make a mistake. Denominator is like this way, And this becomes minus 4 du and dv plus sinh sine u minus v d omega 2 square. Okay, and as we want, so here the reason why I did that, so here u and then and the b are like this way, or since r, we assume that r is equal to positive. Okay, so therefore b has to be greater than u. Okay, and then since the minus infinity, so t minus u and t minus b is minus infinity, so this is infinity and the minus infinity, or maybe like this way. Sorry. So infinity, so therefore this should be equal to pi over 2 and then minus pi over 2. Okay. So this is the region. So therefore, so the reason why we did is that we just really need to repackage minus infinity to infinity to the pi over 2 region. Okay. And what's going to happen is as follows. So then like this way, and then u is like this way. U is equal to 0 is what? This is u equal u direction, and this is b direction. Is it correct? I don't know which one is correct. U is constant means what? T is equal to r plus constant. So therefore opposite. Sorry, I think it's the opposite, right? Is it correct? Which one is correct? Is it correct? U is constant. U is constant means like this way, right? So it's okay. T minus r, T r plus constant, right? So it should be okay. Yeah. So this should be okay. So sorry. Most likely this is also opposite. Sorry. This is most likely this is opposite. This is b, and the u axis. Okay. Like this way, and then Kosa structure is everything repackaged in pi over 2 region. Sorry, pi over the 2 region. Fragile. Like this way. So minus infinity. This is pi over 2. This is pi over 2, and this is minus pi over 2. And the space-time is like this way, and then the t is constant is something like this one. T is constant is something like that. So these are t is equal to small t is constant. Okay, and the r is equals to constant is something like this way. Is the, as you can easily guess, like this way, like this way. So these are the r is equal to constant. So even though space-time is the minus infinity to infinity, we can repackage if you use the arctangent to the pi over 2 region. Okay, so that's the merit of this one. And always the causal structure, light cone is something like at each point represent two spheres. Okay, in this case, so we ignore this part in this diagram. So therefore, it's at each point has a two sphere. Okay, space-time two sphere, and light cone is always something like this one. Always 45 degrees. So this is always light cone. Okay, so these are the causal structure to take a look. Okay, and sometimes terminology, usually future infinity we call it a small I plus. So this is future infinity. And the past infinity we call I minus. Okay, past infinity is, so all the past infinity is just squeezing into the point. Okay, to the point because of this conformal factor. And also, this is I0. This is called space infinity. Okay, space infinity. We have like each point have a sphere, right? So therefore, at each point, really is space infinity. At the sphere become infinity. Okay. What else? Yeah, and then so future light. So the here usually it's called a scribe plus. Script I is in people. I mean, in GR people, it's a common notation. This H is called scribe plus, and this is the future light like infinity. So all the light is will future infinity will hit this edge. Okay, so therefore it's called the future light like infinity.
I'm sorry, isn't it the other way? Like, where the space infinity should be on the bottom and the top corners?
Wait, because I mean this is T.
If this is T, then UV should be different.
Sorry, this is not T is constant. R is equal to constant, right? Sorry. So sorry. Thank you so much. This is R constant. You should tell me. And then that's why he confused. And this is T is constant. So that if you go from this how to say the light green line. So this is minus T equals to infinity, and this is T goes to infinity. Small t goes to infinity, and the R is constant. Sorry. So sorry. You should correct me. And yeah, these are like really the T is constant. T is constant. Sorry. That's why he constant. So this is the really T goes to infinity. All the this green line just converge into this point, and all the line it converge to past infinity. That's why the particle trajectory like this way, okay, and this way, and then so the past light like past infinity is called script minus, scribe minus, script I minus. So people on GR community call scribe minus. So this edge is called scribe minus. Okay, and so on. So that's the people usually used. Since I'm running out of time, so if you use this, that's why I want to keep. Maybe next week I will more carefully write down the change of variable and so on. So if you use the whatever, again, alpha is equal to tangent inverse of u, and beta is equal to tangent inverse of b, then this diagram will look like this way. and then appropriately multiplied some compound factor, it become like this way. So I use the blue one is singularity, and then number 1, number 2, number 3, number 4. Okay, and then what was that? So this t is constant line become like this way. So t is constant line become like this way. These are t is constant line. These are t is constant line. And then r is constant line is something like this way. Okay, and then if you go to number 2 region, as I mentioned, time and the radius direction is swapped. So therefore, something like this way become is so as I mentioned, this r is constant line become like this way, and then r equal to 0 is at the end of the day, r equal to 0 is this one, the singularity. And then t is equal to is like this way. Okay, and appropriate mass by compound factor. So this is the r equal to constant, and t is equal to constant is something like this way. Okay. So these are the Penrose diagram of shear spacetime. And then, yeah, so you can just, event horizon is again this part. And this part, event horizon. And this axis, most likely B corresponds to beta. And this corresponds to alpha, okay? And then you can repackage like pi over 2, and pi over 2, and so on. Minus pi over 2, and then minus pi over 2, and so on, okay? And then people just call, again here, this part is called I plus, I minus, sky plus and sky minus, sorry. So script is very important. And this is I minus, I plus, I 0, and so on. So this part is separate universe, so maybe you can call it some other name, whatever. It's good time to stop. Okay, so let's stop now. It's a good time to stop, and then we'll continue.